Sure. Thank you very much. So, good evening, everybody, and thank you for this talk. My name is Zoe Spetsieri, and I am a postdoc at the National Observatory of Athens. And today I will be speaking to you about the discovery of an optical cocoon tail behind the star HD 185806. This project was funded by the EU, ESPA, and was launched at the National Observatory of Athens. And it was a collaboration between Panagiotis Boumis, Alexandros Chiotelis, Stavros Akras, Sofia Terlopa, and myself. I will give you a brief context about my talk. I will first start with an introduction explaining why we selected to study this source, why it was interesting and worth studying, and then I will proceed to describe the data reduction strategy we followed, because we have both images, which we reduced photometrically, and we obtained spectra, and we also performed a shell spectroscopy on the data. Then I will continue by analyzing our results, and then I will express our conclusions. So this is the star. It's called HD 1858 or 606. It's also known as V1279 Aculae because it's in the constellation of Aculae. The star is the bright source over here at the lower left part. And the peculiar thing about this star is that it's followed by this cocoon-like tail, which displays some very intense filaments, and which at some regions are emitting strongly than in other regions. Now, in general, it's not that uncommon for a star to be surrounded by nebula. However, what is quite rare is these nebular structures to emit in the optical wavelengths, because they are mostly, especially for stars bright as this, they're mostly seen in the infrared wavelengths. So this reason was the main reason that we chose to study this source. This is a very bright source. Its V magnitude, according to the SIMBAD, is approximately 5 magnitudes. And we decided to study the flux, how the flux ranges at this filamentary tail that is following this source. In addition, this source was also in a catalog with runaway stars. So we wanted to investigate whether this star is a runaway star, and that might be the reason it displays this nebular structure behind it. So let's see what our steps were. First of all, we digged into the bibliography, and we saw through the bibliography that this is an M-type long period variable. Gaia DR2 gave us a radial velocity for this star being at 13.8 kilometers per second. From the Gaia radial velocity, we were able to calculate the space velocity of the star, which was 44.9 kilometers per second, approximately 45, meaning that the star had a proper motion and it was moving quite rapidly. And there were also WISE observations. And we had WISE 1, 3, and 2 and 4, which account respectively to 3.4, 12.1, and 22 microns. This was all that there was in the bibliography, and we also searched for additional data by stars that display nebular structures surrounding them and that they were visible in the optical wavelengths. And unfortunately, we didn't find anything more. So we had to perform our own observations on this star. And the 2.4 meter telescope Aristarchos helped us. We used the 3 optical filters, the H alpha, the O3, and the H alpha A2 and the sulfur 2. We performed optical photometry on the images using DALPHOT, and we also collected spectroscopic data through the MES spectrograph, and we performed a shell spectroscopy of those data. I will move on to our photometric results. These 2 images are the products of our photometry. These images are the products after the photometry. I intentionally did not insert the images and how they looked before the photometry. And this is a mosaic created in the O3 filter, where you can evidently see the intense O3 emission of this nebulous structure. Of course, the star is here in the center. And this is the equivalent image in the H alpha. So what I want to point out here that in both filters, O3 and H alpha, you can evidently see the cocoon tail. Its emission is weaker at the H alpha here, but the filamentary structures are quite evident. And what's also very interesting was the flux that was ranging in the filament within these filamentary structures. There were some areas that the flux was higher, of course, here where the emission seemed stronger, and in other areas the emission was weaker. And in general, we performed the flux ranged from 7.5 to 10 to the 12 ergs per second per square centimeter. And the flux of the star, because we also performed photometry on the star where it was possible, at the images that was possible, was around 10 to the minus 13 ergs per second per square centimeter. We also noticed, you must also have noticed that I mentioned 4 filters, and you also see 2 filters here, the O3 and the H alpha. Unfortunately, the filamentary structure was not evident in the other 2 filters, and that's why it's not included in this presentation or in our photometric results. Now, I mentioned also that this source had a photometry, oh no, not a photometry, excuse me, it had imaging through Ys. And the fact that this source was moving and it had a tail puzzled us, because usually when a source is moving in space and you can see the tail of the source, you expect to also see the bow shock that is formed from the source's movement. And although the bow shocks are mainly evident in the infrared filters, since we could see the tail, we were expecting some bow shock evidence in the optical filters. So we saw almost nothing, as you can see in this image, and that is why we tried to construct the RGB image by using the 3 Ys filters, and this was the result. This is the Ys RGB image, where you can see the tail, of course, that is also evident in the optical. This is a cocoon tail, and at the RGB image, you slightly see an emission that is coming from the bow shock, and then you see the star. Of course, the star is super bright, it's saturated here in the Ys image, and you can also see it being very bright with spikes at the optical image. And our main assumption is, so far, that the star's light may be contaminating the bow shock, and that may be the main reason that we cannot that we are not able to see the bow shock in this O3 image. However, we can see the rest of the tail, as you can see it here evidently at the Ys RGB images. And we move on to the spectroscopic results. We also had spectra by the mesh spectrograph for the filaments. These are the 2 slits, slits 1 and slits 2. And here are we marked the regions where we took the spectra with the letters A, B, C, D, E, F. You see that we tried to cover the whole filamentary structure from top to bottom. And we performed the shell spectroscopy in order to calculate the heliocentric velocity of the nebular structure. And this is the table with our results. It's the results are ranked per slit and per filter, but in general, the nebular tail has a velocity ranging from -100 to approximately 35 kilometers per second, 35 to 40, which is mainly acceptable, because that means that the structure is expanding, and in parallel it's moving with the star. We also constructed the position velocity diagrams per slit and again per filter. This is for the first slit, for slit 1, which corresponds to, excuse me, this slit over here. So you can see the regions A, B, and C in slit 1. And in red arrows, which are not that evident in this presentation, are the positions A, B, and C. At the position velocity diagram, we mark that the emission in the H alpha is stronger in the edges than it is in the center of the filament. This is the N2 filter, where the emission is almost confused with the main background, but at the edges, at the positions A and C, you can evidently see that there is something there, so you couldn't ignore that there was emission at the N2 at slit 1. However, at slit 2, things become more precise because, again, we have strong emission at the H alpha, and then here comes the O3 that we see that the nebula emits strongly. And these are the positions D, E, and F. Again, we see that the edges emit strongly in comparison to the center of the nebula. And we also see a symmetry between equivalent filters. For example, this is the H alpha and this is the H alpha. Again, this symmetry is because of due to the positions of the spectra that we took. And after calculating the velocity of the tail, we tried to find out more characteristics and properties of the star itself. Unfortunately, our data didn't help much for that purpose, and that is why we used theoretical data. We used the VOSA database and libraries that helped us construct the spectral energy distribution for the source by using all photometric data available, because VOSA contained everything from 2-mass, IRAS, WISE, Gaia data. And this is a spectral energy distribution showing all the photometric data. We see that the star mainly gains energy from the infrared bands, from 2-mass. Using that data, we then applied a fit using the Coelho synthetic library, which mostly accounted for our start. It gave us the best fit. Of course, it didn't fit the whole data range because we were interested in mostly the optical. And that's why we used this fit. But the spectral energy distribution gave us a temperature ranging from 3200 to 3400 Kelvin approximately. And after having an assumption about the temperature, we tried to figure out the mass of the star, and through the mass, figure out the evolutionary state, what state that star was. So we decided to plot the temperature and the luminosity on an HR diagram, and then overplot MESA evolutionary models and see which model fitted better. And we found that the best fitting model was the one of the 1.3 solar mass star. So we concluded that this evolutionary track fitted better. Of course, this is theoretical. And we also try to determine the phase of the star, and we color coded the different phases based on the model. And as you can see, our star resides over here, which is the post-AGB phase. Now, it's quite arbitrary to define a star between an AGB or a post-AGB star. So according to the mass loss rate given by the model, we assume that the star is in the transition phase between the thermal pulsating AGB and the post-AGB phase. Something which is also aligned with the theory and the fact that AGB stars expel material, have strong driven winds that could interact with the circumstellar medium and shape and form bow shocks and nebula around the stars. So this evolutionary track, to be honest, quite fits in the results. And to get back to the bow shock that I was mentioning before, having the nature of the star in the phase being an AGB or a post-AGB stars, we tried to apply a simulation to see whether the bow shock would be evident if the star was an AGB or a post-AGB star, and I will explain what I mean. Now, in order to see the bow shock must be in a certain distance relatively to the star. That distance is stated as the stagnation point. And in some cases, when the wind velocity and the ISM are quite dense, the stagnation point is not evident. And these are the simulations that we performed for various wind velocities that according to the theory, may apply to AGB or post-AGB stars. And for different values of ISM densities, we tried to plot the stagnation point relation and see whether it's evident or not. Now, the red dashed line indicates whether the stagnation point is evident. If the lines, the other three lines are upon the lines, it is evident. If it's below, then it's not. And as you can see, in most cases, the IS of the ISM density being 1 in 10, you see that we cannot see the stagnation point. So this is a parameter that also matches our theory, along with the fact that in the optical images, we can't see it because the starlight contaminates it, and that's why we can't see the bow shock. And after analyzing the star, we returned to the shell, to the cocoon shell, and our colleague, Sofia Del Loco, which is a shape model expert, was kind enough to perform a 3D morphokinematic modeling of the star, so we can see how the star with a shell moves in space. And at the first image, you see that the model is an ellipsoidal model. Here are the two slit positions, slit 1 and 2. And in this image, you can see the blue arrows that indicate the movement of the star in space. The front part, this is the star. The red dot over here indicates the star. And you see that the star is getting away from us, while the other arrows show that the nebula is coming towards us, which is something that we expect. And at the images below, you can see the position velocity diagrams of the spectra in the H alpha and O3. The blue line here indicates the blue shifted region, and the red line indicates the red shifted region. And to reach the conclusions, we found through our study that the star is an M-type star at an AGB or post-AGB phase. We optically identified a cocoon tail surrounding the source. We confirmed through our result that there is an interaction between the stellar wind and the motion with the surrounding circumstellar medium. We performed the spectroscopy and found that the nebula has a velocity between -100 to 40 kilometers per second. And the systemic velocity was around 45 kilometers per second. And the 3D morphokinematic model showed an almost ellipsoidal structure with a position angle of approximately 19 degrees with the plane of the sky. Thank you very much.